Hello everyone, my name is Oz. We will talk about Lattice Boltzmann method today. Here our outline. It's comprised of introduction section, historical perspective, general principles, governing equations, hand calculation example and numerical example. And at the final section, we will talk about example applications and conclusions. In introduction section, we will provide context to the method. How is it different from the others? In what situations does it perform best? Are there special features of note? And are there particular shortcomings? For the context, the Lattice-Boltzmann method is a computational technique used to simulate fluid dynamics and other complex physical systems. It models fluid flow by tracking particle distribution functions on a discrete lattice, evolving them via collision and streaming steps. When we rooted in kinetic theory, Lattice-Boltzmann method breeds microscopic particle behavior, like the Boltzmann equation, with the macroscopic fluid properties like Navier-Stokes equations. It is particularly popular in computational fluid dynamics and soft matter physics. For the differences between other methods and Lattice-Boltzmann method, for the finite element method, it solves partial differential equations on unstructured meshes, focusing on continuum mechanics. Lattice-Boltzmann method also uses a fixed lattice and statistical approach, avoiding direct partial differential equation solving. For the discrete element method, it tracks individual particles with contact mechanics, ideal for granular flows. Lattice-Boltzmann method treats fluids statistically, not particle by particle. For the phase field methods, this model interfaces, for example, phase boundaries via continuous fields. Lattice-Boltzmann method excels at sharp interfaces and multi-phase flows without explicit field equations. For the smoothed particle hydrodynamics, it's mesh-free and Lagrangian, tracking fluid particles. Lattice-Boltzmann method is Eulerian, lattice-based, and inherently parallelizable. For discrete lattice spring method, it simulates solids with spring-like interactions. Lattice-Boltzmann method focuses on fluids and soft matter using a kinetic framework. The Lattice-Boltzmann method offers a unique kinetic-based approach to fluids simulation, standing apart from continuum finite element method, the particle discrete element method, and smoothed particle hydrodynamics, or interface, which is phase field methods. It shines in complex multi-phase flows and parallel computing tasks, but traits adaptability for simplicity and lattice dependence. For the best performance of Lattice-Boltzmann method, it excels in porous media, microfluidics, and flows with the intricate boundaries due to its simple boundary handling. It's ideal for simulating bubbles, droplets, or emulsions as oil-water systems. It thrives in high-performance computing environments due to its local grid-based operations. It breeds micro and macro scales, making it perfect for systems like colloidal suspensions or biological fluids. For its features, Actually, it's easy to implement with a regular lattice. Collision streaming steps are computationally lightweight. Also, local rules allow massive parallelization, unlike finite element methods' global matrix solving. It incorporates microscopic effects without extra complexity, like thermal fluctuations. Also, it extends to non-Newtonian fluids, turbulence, and reactive flows with modifications. For the shortcomings, actually, it is fixed grid, so it limits resolution and adaptability compared to finite element method or smoothed particle hydrodynamics flexibility. It struggles with stability in turbulent flows unless enhanced, for example, with multi-grid techniques. It requires storing distribution functions at each lattice point, increasing memory use over traditional computational fluid dynamic methods. It is less suited for structural analysis compared to finite element method or discrete lattice spring method, as it is fluid focused. So for the historical perspective, we will look at what are the origins of the method, when was it developed and by whom, why was it developed, what significant evolution has it gone through. So, for the roots in kinetic theory, the Lattice-Boltzmann method originates from the Boltzmann equation, which describes particle dynamics statistically at the microscopic level. It adapts this to simulate macroscopic fluid behavior. For its predecessor, it emerged from lattice gas automata, a discrete model of particle collisions on a grid. It was introduced in the 1980s. So lattice gas automata inspired LBM's lattice-based framework. So for the development, so actually its timeline, so LBM was formalized in the late 1980s to early 1990s with key developments around 1988 and 1992. So its key contributors, so Genevieve Higuera and Saura Suki in 1988, they are early pioneers who transitioned LGA to a continuous distribution function approach. After that, Kian de Humiere and L'Element in 1992, they introduced the widely used D2Q9 model, which is 2D 9 velocities, standardizing LBM for fluid dynamics. For the collaborative effort, it grew through the contributions from computational physicists and engineers globally. It was born from lattice gas automata in 1980s, formalized by Suki Kian and others in the 1990s. Lattice-Boltzmann method evolved into a powerful tool for fluid dynamics. So, because of this, it matters. It developed to simplify complex flow simulations. It has grown versatile, tackling everything from microfluidics to turbulence, driven by computational advances. So, for the reasons, our main purpose is that Lattice-Boltzmann method was created to overcome limitations of lattice gas automata, which suffered from noise and complexity in recovering Navier-Stokes equations. So for the goals, there are many goals. So those are simplifying fluid simulations with a more efficient, less noisy method, bridging microscale kinetics and macroscale hydrodynamics, enabling simulations of complex flows, for example, multiphase porous media, impractical with traditional computational fluid dynamics methods like finite differences. For its evolution, for the early stage, it shifted from binary LGA to continuous distribution functions, improving accuracy and stability. The Batnagar-Gross collision model in 1990s simplified the computations. For its expansion, it adapted for multiphase flows, thermal effects, and non-Newtonian fluids. Models like Shan-Chan in 1993 enabled multiphase simulations. For the modern advances from the 2010s to our present days, it enhancing the turbulence modeling like large eddy simulation with Lattice Boltzmann method. It coupled with other methods, for example, Lattice Boltzmann method, finite element hybrids for fluid structure interactions. Also, it optimized for GPUs, boosting performance in large-scale simulations.
Hello, this is Maher. I will present the general principle of the Lattice-Boltzmann method. Let's begin by introducing the Lattice-Boltzmann method, or LBM. LBM is a computational approach used to simulate how fluids like air and water move. What makes it unique is that instead of solving the Navier-Stokes equation directly, like traditional fluid dynamics method, LBM tracks simplified fluids behavior using particles that live on a grid. These particles follow simple rules. They stream in specific directions and collide locally at each time steps. LBM belongs to a class of models that operate at the mesoscopic scale. This means it doesn't track every individual molecule like in microscopic models, and it doesn't treat fluids as a continuous bulk material like in macroscopic models. Instead, LBM represents fluid as particle distribution function at each node in a grid. These distributions describe the motion and properties of the fluid. To better understand LBM's place in simulation methods, think of three physical scales: the microscopic, where individual molecules are tracked; the macroscopic, where continuum equations like Navier-Stokes are solved; and the mesoscopic, where LBM fits. LBM bridges the two scales, offering a unique balance between physical realism and computational simplicity. Let's compare this briefly to the Navier-Stokes approach. Navier-Stokes equations describe fluid motions using partial differential equations that are solved at the macroscopic scales. These methods are mathematically widely used in engineering, but they require solving large system of equations, which can be intensive, especially for complex boundaries or multi-phases flows. LBM avoid this complexity by relying on simple local interactions. It simulates the same fluid behavior without solving differential equation directly, which makes it easier to implement. One of the key strengths of LBM is its simplicity. The, the role governing the roles governing particles movement and collisions are local and uniform. Each node in the grid updates based on a small set of directions and interactions. LBM is also extremely flexible. It can easily handle complex boundary conditions, such as curved surface, porous media, and multiple interacting fluid phases. This allows LBM to perform well in domains where traditional methods may struggle. Now let's dive into how LBM actually represents fluid flow. We begin on the left with a basic view of fluid as a random collection of particles. Each dot in the image represents a particle moving around freely in various directions. In reality, fluids behave as a collection of countless particles, but following every particle would be computationally impractical. So in LBM, we use a grid average out particle behavior. Each node acts like a window where we observe groups of particles moving in certain directions. In LBM, instead of tracking each particle individually, we place them onto a structured grid, as shown in the middle image. Each square or node in this grid is a special location where we track a distribution of particles. This simplifies the model significantly while preserving important features of the flow. Zooming into one of these nodes on the right, we see what's known as D2Q9 model. D2Q9 stands for 2 dimensions and 9 directions. This model is commonly used in 2D simulations. At each node, particles can move in one of 9 discrete directions: to the left, right, up, down along the 4 diagonals, or they can remain stationary. These predefined directions simplify the streaming process and make computations very efficient. The D2Q9 layout ensures symmetry and conservation. Symmetry means the fluid behaves the same in all directions, which is important for accurate physics. It also ensures that mass and momentum are conserved. So during simulation, what happens is this: particles at node collide and redistribute. This is collision step, and then they stream to neighboring nodes along these 9 directions. This repeating process of local collisions and movement across the grid forms the foundation of the LBM. The combination of the particle lattice structure and discrete directions makes LBM both simple and powerful when it comes to simulating complex fluid behavior. This slide walks us through the full simulation loop of the Lattice Boltzmann method. We begin at the top left with initialization. In this step, we define the size of the grid, the number of nodes, and the time step. We also assign values for fluid properties such as density and velocity. Then we initialize the distribution functions at each node. These distributions represent how particles are spread in each of the 9 directions. If the fluid initially at rest, these values are usually symmetric. Once the simulation begins, we enter the collision step. Here we use relaxation rules that update the particle distribution at each node. The idea is to gradually shift the particle distribution toward a local equilibrium. This models how real fluid particles would interact, transferring momentum and energy. Next is the streaming step. Each distribution function moves to neighboring node based on its direction. For example, a particle set to move right will go to the node to its immediate right. This allows the information about flow to propagate through the grid over time. After streaming, we move in to apply boundary conditions. In real world problems, fluids interact with boundaries, walls, inlets, and outlets. So we need to define how the simulated particles behave when they encounter these limits. Then we compute macroscopic quantities. Although we are tracking particles distribution, we know physical properties like fluid density and velocity. At each node, we calculate these values by summing the contribution of all particles directions. Finally, we reach the loop to next time step phase. After updating the entire grid, we repeat the cycle for the next time step. This loop continue until the simulation reaches the desired final time or reaches a steady state. Through this cycle of collision, streaming, boundary handling, and macroscopic calculations, LBM simulated fluid flow using simple rules that are fast to compute and still produce realistic behavior.
So now let's talk about the new part, which is governing equations. So here, what we need to know is that Boltzmann method is not a traditional approach that directly solves the Navier-Stokes equations, but instead it models fluid dynamics by discrediting the Boltzmann equation on a lattice grid, providing a mesoscopic description of fluid behavior. So the traditional methods like these FDM, FEM, VM, they solve the Navier-Stokes equations directly, but the Navier-Stokes equations describe a temporal and spatial evolution of density, momentum, and energy. They can be solved in a Lagrangian or Euler framework, just like these methods FDM, FEM, or FPM, depending on the problem to study. In these equations, density and velocity are continuous macroscopic variables, which implies that they can be described by continuous functions. We can measure them by means of appropriate instruments at human scales. But for LBM methods, why it attracts many researchers and engineers? That's because it allows the incorporation of a lot of physical manifolds behaviors become accessible, like turbulence, acoustics, phase transition, and thermal fluids. It is used in the field of safety modeling for transport, storage, and other topics. So LBM method is very well suited for scientific safety computing with GPU. So here, fluid seen at its microscope scale is an ensemble of molecules which have an unexpected behavior and unpredictable behavior. We cannot just ignore that. Establishing links between micro and the macro scales improves our understanding of the fluid behavior, and thus we may become able to use this knowledge to improve current known methods. So here is some questions. What are the big problems with the microscopic scale? How can we define the density? How can we define the velocity? And what's the link between the movements of particles and the absorbed properties of the fluid? So here we see this equation, which is defined the density of the at the particle level. So the density is simplified the total mass packed into a certain space. This is a physical foundation of how LBM method models follow by counting how many particles move in and move out of a given region. So here I give an example, which is the L in a room. So now imagine a quiet room with no window open. You don't feel any wind, so the L seems still. But microscopically, L molecules are moving very fast, constantly bouncing and colding. So why do we feel no motion? This leads to the key concept, which is isotropic. It means that the probability of a particle moving in any direction is the same because of this direction symmetry. The net effect of all particle motion cancel out, and the microscopic velocity is zero, even though there's intense microscopic activity. So to summarize here, that isotropic equal to same probability in all directions equal to macroscopic velocity is zero. And as for how fast the particle are moving, we describe these with a distribution function, used written as a f function equation. So, which tell us how many particles have a given velocity at a position. To find the probability that a particle has a speed between A and B, we use this equation at the bottom. So this gives us the fraction of particles with speed in that range. So in this process, we also need to consider the temperature, because when the temperature change, the velocity will also change. But here let's talk about the example first. So for the kinetic energy, a bullet has a high speed after detonation, and therefore high kinetic energy, which can cause damage. Now, zooming into the microscopic world, gas particles behave similarly. They are like millions of tiny bullets, all moving in different directions. Boltzmann showed that this motion, this average kinetic energy, is directly linked to temperature. So when we measure temperature, we are really measuring the average motion of all these particles. That's why high temperatures mean particles move fast, and why a hot gas has a broader and faster speed distribution than a cool one. And you can see this kinetic function here. In this expression, the constant Kb has appeared. This is a fundamental constant called the Boltzmann's constant. The kinetic energy AC we get is in fact called the internal microscopic energy, as it contains the energy of the particles. And here shows the particle position and the particle's velocity maximum distribution. The mean average may be fixed, but nevertheless, all particles of an isotropic mass don't necessarily have the same kinetic energy. So to deal with the problem of speed and magnitude distribution, we assume that a particle can have any kinetic energy as long as the mean kinetic energy of the set of particles allows us to reconstruct a physical coherent macroscopic temperature when summing over all the particles. So for the distribution of the speed and magnitudes, if we consider that each particles individually notice velocity according to an individual in determining the probability law, the central limit thermal teaches us that for a large number of particles, the distribution law to be globally applied is the Gaussian normal law. Thus, the distribution of speed and magnitudes is done according to the normal law right in here. You can see this function. So this distribution law is called the Maxwell equilibrium distribution, valid for a perfect gas. The constant Rs is the specific gas constant, T is the temperature. E is the microscopic velocity of particles, and U is the macroscopic velocity. I use this formula and for a fluid at rest, Vostorian sum of velocities is known. At the macroscopic scale, each particle has a certain velocity, which is not known. Velocity is linked to kinetic energy, which is linked to temperature. The velocities of all the particles can be represented by the Maxwell equilibrium distribution for a perfect gas. So now let's talk phase space. This is a crucial concept in kinetic theory and the Lattice Boltzmann method. In regular geometry space, we describe a particle's location with three coordinates, x, y, and z. But let's all in part of the story to understand how particles behave, especially in terms of energy, pressure, and follow. We also need to know their velocity, how fast and in which direction they are moving. So we combine position and velocity into one large space, phase space. In this space, every point represents a complete snapshot of a particle's state, both where it is and how it's moving. And because system evolve, we also include time, so the full description involves position, velocity, and time. This concept is fundamental to the LBM framework, where we mold how particle distribution evolve over space and time. Earlier, we introduced the Maxwell distribution, which helps us describe particle behavior at steady state. But real-world fluid systems are rarely in equilibrium. If we only study equilibrium properties, we miss out on the dynamic nature of most fluid turbulence, shock waves, and the boundary layer effect, for example. So how do we move beyond the steady state? We do this by defining a distribution function in phase space, denoted as fxat. This function gives us the probability of finding a particle at a certain position x with a certain velocity e at a given time t. It's a way to capture both the spatial and the kinetic aspects of particle behavior as they evolve over time. This is exactly what we need in Lattice Boltzmann method, a model that let us check how this distribution change in response to cohesions, forces, and boundary conditions. So now that we have defined the distribution function fxat, how do we describe its in evolution? Let's start with a simple case. So low match number and no cohesions under these conditions. The total derived derivative of f is conserved. This means the function is transported along the particle's trajectory. Mathematically, this is written as the first equations. So these equations describe the vector of particles in phase space. So to make this to make this usable in a numerical scheme, we apply a Taylor expansion over a small time step delta t. So this gives us a discrete update loop. So what is the second function? So this handles pure transport, but in reality, particles also correlate. So to model this, we introduce a correlation operator, in the smallest approximation known as BGK, the post-cohesion distribution relaxed toward equilibrium, which showed this function. This is a famous lattice Boltzmann equation. It includes two key steps: cohesion, which particles relax toward equilibrium, and streaming, which where particles move to neighbor nodes. So these two steps are the foundation of LBM algorithm. So in continuous Boltzmann equation, particles can have any velocity, but to make the problem traceable for numerical methods like LBM, we describe the velocity space. This means we limited particles to only a finite number to descriptions of finite number of directions. A widely used example is the D2Q9 lattice. D2 stands for two spatial dimensions, and Q9 means we use 9 discrete velocity directions. These include 1 zero velocity rest direction, 4 direction points pointing to the cardinal points north, south, east, and west, and 4 diagonal directions. In general, we refer to LBM lattice using the DNQM notation, where m is the number of spatial dimensions and m is the number of discrete velocities. At each node in lattice represents by blocked dots. It isn't just one particle, but a whole population of particles moving in these discrete directions. The number of particles moving in each direction determines the local distribution function and is directly tied to macroscopic properties like density and velocity. This discrete framework is what will allow us to apply the lattice Boltzmann method efficiently to simulate fluid flows. So now that we have defined the discrete velocity sets and the phase space discretization, we are ready to introduce the discrete Boltzmann equation used in LBM. For each direction I, the LBM can be written with two clear paths. On the left, we have the streaming term. It represents the motion of particles along discrete directions. On the right, we have the cohesion term, which brings the particle distribution back towards equilibrium. This is what models viscosity and reactions. To control the speed of these relaxation, we defined a relaxation parameter omega. So the inverse of relaxation time tau, this allows us to rewrite the LBM in a more compact form. This equation underpins the entire LBM algorithm, which runs in 4 simple steps. Correlate string, apply boundary conditions, and update the macroscopic variables like density and velocity. This combination of velocity of local computation and simple transport makes LBM highly parallelizable and efficient for simulating fluid flows. Yeah.
Hi everyone, I'm Fan Fan and I'm going to show an example on how we can implement lattice Boltzmann method to solve different problems. So I'm going to use a simple heat diffusion and a division problem in one-dimensional medium. That here is the question. We need to consider a flow in one-dimensional porous medium of 4 meter long, and the value of phi, which stands for the temperature, is 300 Kelvin throughout the domain. At the left-hand side, boundary condition for phi is 500 K. So the velocity field of U equals to 0.1 is kept constant in the domain. The thermal diffusivity of the following material is set to 0.25 meter square per hour and does not change with the temperature. And the advection and diffusion equation is one-dimensional. In one-dimensional is given by this equation. And our task is to calculate the temperature distribution in the domain after 4 hours. Here is the calculation steps for this problem, and also that is the hand calculation steps we calculated in the following slides. And firstly, we need to initialize this problem. We need to normalize and scale the parameters involved in this problem, and we need to discretization of the domain into lattice. In our case, I divided the domain into 4 lattice, and each lattice stands for 1 meter. And then we need to calculate the equivalent distribution function for each lattice. And the function and the equation function we stick to is listed here, and the omega k stands for the weighting factor, and the phi here is the temperature in our case, and the blasket term here means describes the motion of the lattice, the motion of the phi move. So in our one-dimensional case, there is only 3 options that like the to the right and to the left stay stable. And so it corresponding to +1, -1, and stable, and 0. And the third step is the collision. The equation here involved in this calculation is listed here. The omega here means the relaxation time for the for this domain, and the fourth step is the streaming step. It describes how the lattice influences the lattice around it. The adjacent lattice. And then we need to apply the boundary conditions. In our case, because the temperature constraint is applied at the left boundary, so the boundary conditions meaning influence the left the first lattice, and then we need to calculate the macroscopic values. It means we need to transform our this dimensionless value into macroscopic values, and then we need to return to the second steps till we finish all the 10 steps, and then we got to the output. Here we So here is the discrimination of the domain into lattice. In this problem, we are going to use full lattice of 1 meter each, as shown in the figure, and the X pre, T pre, and the capital T and alpha pre are all the non-dimensional normalized terms. X pre stands for the distance or the length of the domain, and the T pre means the total time means the non-dimensional time, and the capture T means the temperature at any given time. And by normalize it, we can control all the values change from 0 to 1, which can reduce our calculation efforts and can make our communication more easier. And the alpha prime means the value for the sum diffuse velocity, and the omega means the relegation time for this problem. And in this slide, you will see for lattice their distribute functions. The F1 here means the distribute functions towards the positive direction, and the F2 means towards the negative direction if we make the right one is the positive direction, and the 0 means the distribution function stands still. And for the D1Q3 lattice problems, the weighting functions for each lattice are constants. So for the omega 0, which means the weighting function for stands still, it is 4/6, and for the left or for the right, they are all 1/6. And for the dimension is temperature at each lattice. We can because we can calculate it according to this equation. So we will keep it between 0 and 1. And then we came to the initial distribution function in lattice. Because because initially the temperature at in the domain is zero, and we only have the temperature at the left boundary. So the F0, so the F value and the equivalent value for each lattice are all 0, and but for the first lattice, because it has a left boundary of a constant temperature, so the F1 of it is 1. And as the first time step, there is a we can say that for the first lattice, we need to calculate its equivalent function according to the 5 values of last step, which means 1, and we need to assign the energy distribution according to the weighting factors. In our case is these 3 numbers. So we we calculated and listed as the table. And then we perform the collision for each lattice. It will the FK here means the allergy distribution of last step. In our case, is we can say the previous slice is 0, 1, 0. So we need so we can calculate the allergy distribution, which means the lattice the allergy direct the allergy value in each directions for the lattice 1. And then we came to the streaming step. The streaming step means how the lattice influence the next lattice, and it will stick to these 3 equations. For the F0, it will remains the same, and for the F1, it will like just right to the next lattice, right? And for the left value, it will comes from the second lattice, so it will stream like this. And for our hand calculation example, what we do is like we cycle shift the F1 value to the right, and we cycle shift our F2 value to the left. And so we got this table. And for the second 10 step and the following 10 step, what we do is similar. So at the second 10 step, we need to recalculate the equivalent function for each lattice, because from the previous step, we can say the phi value for each lattice has changed. The phi value is the sum of F0, F1, and F2. So we need to reassign the phi into different directions according to the weighting factors, and then we will got the equivalent value of the lattice 2. And what we need to notice that we also need to recalculate the lattice 1, because that phi for lattice 1 has already reduced. And then we need to perform the collision step according to this equation. The F value here is the phi value at the last 10 step. So we can say here I list the specific calculation step, and you can say this column here is the table here. And the second part of the collision is the equivalent function value for each lattice. That is what we calculated here. And then we can got this table. So this calculation what it mainly do is like the equivalent function tells you how the lattice tend to get the allergy value for each lattice tend to get. This is an ideal state, but after collision, the equivalent function will influence it, but will influence it at a weighting factor of omega, but it will also affected by the next step. By the next step, the real function value. So I feel like it's like it's like a redistribution towards the direction of the equivalent. So it's like multiple influence of the influence of each other, and then we came to the stream step. For the stream step, what we do is like cycle shift it to the right, and cycle shift this f2 value to the left, and then we got this table, and then we need to apply the boundary condition, because the lattice one is the phi value for this lattice one is always one. Remember that we have a constant temperature at the left boundary, so this value should be summed up to 1. So we can calculate the f1 value here, and then we came to the third step. It's quite similar. We should calculate the equivalent function for each lattice, and then we perform the collision step, and I list the results in this table, and you can see the specific calculation here, and then we should perform the steaming step. That one is also like a repetition. What is different that is we need to apply the boundary condition to recalculate the lattice 1 f1, and then we came to the last time step. This is repeatedly, and you need to recalculate the equivalent state for each lattice, and then you and then when the lattice collision, you should recalculate the allergy function, the allergy distribution after their collision according to the influenced both by their by their last step allergy, and also the equivalent state function allergy, and at the last step, when we perform the streaming, because here we got the phi value distribution like this, and what needs noticed is that because is that the for the lattice one we like always keep it to keep the f value sum up to 1 as 0, but for the right boundary, because it's an open boundary, and so when we cycle shift the omega value of lattice 4 to the lattice 3, we need to consider that the lattice 3 value has already like conveyed to the fourth lattice, because we don't want any temperature discontinuity in this domain. So here the lattice full for its f2 is 0.0195, and once we got the omega distribution, and the sum of the f1, f0, f2 is the phi value. Is a phi value for each lattice. And in our case, the phi value means the temperature. So we can calculate the microscope temperature of each lattice according to these equations, according to the non-dimensional temperatures definition, and then we got the temperature distribution for each lattice, and that is how we solved this problem, and based on the Boltzmann method. And so you can say the temperature distribution after 4 hours in our example. That's all.
Hello everyone. Today I'll walk you through our numerical simulation example, which is a well-known benchmark, the lid-driven cavity flow, using LBM in MATLAB. We'll cover the setup, the code, and the results. Our goal here is to validate the LBM approach using a well-known benchmark, which is the lid-driven cavity flow. We'll be using the D2Q9 lattice scheme in MATLAB and observe if it captures the characteristics vertex inside the cavity. In this simulation, we set up a 2D square cavity. The top wall moves while the others remain stationary. This movement generates recirculating flow. We expect to observe a stable vortex at the center for RE of 100. Before we simulate flow, we initialize the entire fluid domain. We start with the uniform density and zero velocity everywhere. Each node is assigned a distribution function aligned with the D2Q9 velocity directions. We used a 100 by 100 grid and simulated 50,000 steps. The top wall was given a constant velocity, while bounce-back conditions maintained no slip at other walls. Streamlines were used to visualize the flow. Each time step, we apply the collision step, where each particle distribution relaxes towards an equilibrium based on the current velocity and density. After collision, we stream the distributions in the direction of the respective velocities to neighboring nodes. This is key to capturing fluid behavior. Boundary conditions are crucial. We apply a constant rightward velocity to the top lid and bounce-back conditions to the stationary walls. This setup ensures realistic, shear-driven flow and proper enforcement of the no-slip condition. The streamline plot reveals the expected clockwise vortex. In this result, it confirms that our boundary conditions and numerical method are correctly implemented and that fluid recirculates in the response to the lid motion. The result matches known CFD solutions for Re equals to 100. It shows that LBM, even with a relatively simple implementation, it is capable of accurately capturing complex, incompressible float behavior. In summary, this example successfully demonstrates how Lattice-Boltzmann method can be implemented in MATLAB to solve a lattice-driven cavity flow problem. We were able to reproduce the expected vortex structure at the moderate Reynolds numbers using a clean and efficient LBM formulation. These results validate both the stability and accuracy of LBM for incompressible fluid simulations in bounded domains. This sets a strong foundation for applying LBM to more complex cases. With the basic model working, we can now confidently move on to more advanced applications of LBM, such as multiphase flow and porous media transport, microfluidics, and even aeroacoustics. Let's explore how LBM extend to those scenarios next. As discussed, we will explore how this powerful simulation tool is applied across a wide variety of fields, from traditional fluid mechanics in porous media to cutting-edge applications in biomedical engineering and noise prediction. One of the strongest uses for LBM is in porous media. It is particularly valuable for simulating fluid flow through rock, soil, or filtration media. LBM can work directly on voxel data from CT scan, making it easy to model real rock microstructures. Using 3D lattice models like D3Q19, it captures both Darcy and non-Darcy flow. These features are critical when modeling oil recovery in tight formations or carbon storage in geological reservoirs. Next, we have microfluidics, the study of fluid flow in micrometer scale devices. LBM is ideal for this domain because it handles low Reynolds number flow very well. It also supports both slip and no-slip boundary conditions and can incorporate electrokinetic forces which are common in lab-on-a-chip systems. This makes it an excellent tool for simulating droplet manipulation, particle sorting, and even electroosmotic transport, such as DNA separation. The third major application is aeroacoustics, or flow-induced noise. Traditional CFD struggles with capturing the unsteady compressible behavior needed to simulate sound waves. LBM, particularly in low-match or hybrid forms, can accurately simulate both turbulent source of the noise and the propagation of sound. This is very valuable in aircraft design, for example, when studying how landing gear generates tonal noise. In multi-phase systems, LBM can track the evolution of interfaces between fluids, such as bubbles or droplets, with detailed physics like surface tension and phase separation inherently included. LBM can be extended to simulate heat transfer along with fluid flow, making it a good candidate for simulating convective cooling in electronics or thermal management systems. Another major application is blood flow simulation. LBM has proven powerful in simulating biological flows, such as blood through capillaries. Its ability to couple with structural solvers makes it ideal for studying complex interactions between cells and fluid. To wrap up, LBM is versatile, scalable method suitable for a wide range of fluid-related phenomena. Its mesoscopic nature and compatibility with GPU-based parallelism make it an attractive option for modern simulations. It is encouraged to explore open sources LBM tools to see what's possible in real-world scenarios. Thank you for your attention, and I hope now you know more about LBM. Following this, you will find our references, and also you can find our quiz questions. Thank you for your time.